Good morning, guys. Welcome, and finally I've been able to put up a tutorial on calculus. Now hopefully you have a basic introduction of calculus and what calculus is, but if you don't worry, we're going to cover everything this morning. I'm going to start off with this little picture here that I found on Google. I think it's fantastic. It's got a lot of the main concepts about what calculus is, and I would like to talk about that just very briefly. A couple of really big words here. Derivative, differentiation above it, integral, function, nice big important one, slope. Okay, so all very important words when we talk about calculus. Limits is another one which is very important. So what is calculus? Basically when we talk about calculus, we talk about change. Okay, if you think about when we've done our straight lines, our linear work on algebra, when we talk about the rate of change, we talk about the slope or the gradient of a line. What we'll be talking about today, particularly, we'll be looking at derivatives and differentiation, which talks about the slope or talks about the rate of change of a curve, not of a straight line, but of a curved line. Now in year 11 we'll be focusing on derivative, okay, and then year 12 we'll be focusing on integrals or integration. But basically, as I said, calculus is to do with change. There's lots of different types of calculus, but as I said, we'll be dealing today with the differentiation or derivatives from first principles. What I wanted to start off with is just looking at a normal linear equation or a straight line and looking at how it's written, because sometimes when we're looking at calculus we write it a little bit differently. If we ask to graph the graph of y equals x, hopefully you'll just realize that looks like the graph of y equals x. For example, that might be the point 1, 1. Okay, sometimes we don't actually write it as y equals x, sometimes we can write it a little bit differently. We can write f of x is equal to x. Okay, f of x is equal to x. Now that means the same thing as y equals x. It's just showing you what you have substituted into your equation. For example, if I said f of 1, okay, that would equal 1. So I substitute 1 in there. F of 4 would be 4. If my equation was f of x equals x plus 3, then f of 1 would be 1 plus 3, which equals 4. Okay, it basically means your function of x, which basically means your y value. Okay, what your y value will equal when you substitute your x value into it. If I wanted to talk about a particular point on this graph, often we would talk about it as the point xy, which means we've gone across x distance and then we've gone up y distance. If I want to talk about this in terms of f of x, we could say we've gone across x and then we've gone up f of x. So you can see it basically means the same as that y value. Okay, it's not much difference to that, but it's just a little bit of different style of writing it. And it is important because when we come into our calculus, particularly from differentiation from first principles, we do use f of x a lot more regularly than what we have used in the past. Something else I want to talk about as well, just before we go on, we've spoken about the rate of change, particularly with linear equations, talking about the slope of a line. Hopefully you remember the slope of a line or the rate of change, we're referring to the gradient or how steep a line is. Lots of different ways we can write the gradient or find the gradient. The most famous one, I guess, is our rise over run. Also y2 minus y1 over x2 minus x1. Sometimes also people put delta y over delta x, which means the change in y values over the change in x values. But again, it simply looks at basically having two coordinates on our straight line and either using our rise over run method or our y2 minus y1 method where we're substituting two coordinates into it, and that gives me my rate of change or my gradient or my slope. So that's what basic calculus looks at. Well, differentiation looks at. It looks at, as I said, finding the steepness, the slope of a straight line or the line to the curve. Now it's slightly different because if we look at this particular parabola, this is a nice curve, and often we will look at parabolas when we're looking at this sort of work. I've drawn in a tangent. Now the reason I've drawn in a tangent is because the tangent can sort of show me at a particular point how steep that point is going to be, or that curve is going to be at that point. But what you might notice, if I perhaps take a different point, for example this part of the line, what you'll notice as we're increasing or going, x values are getting bigger, my line, my curve is getting steeper. For example, if I look at that point that I've just drawn on there now, and I draw a tangent, because again, that reflects, although it's not a very straight line, that reflects the steepness of that particular straight line or that point of the curve, you can see that my straight line or my gradient is slightly bigger. Let's have a look if I take one up here. Again, if I draw a straight line, which again tries to show the steepness of the curve at that point, you can see again that my gradient is slightly even steeper. Likewise, if I took the gradient at the bottom of my curve, it would be a nice flat line, which would give you basically a gradient of 0. So the problems that we have when finding the gradient of a curve, that it's not constant. It's not that simple straight line that we're used to. So a curve is constantly changing. It's either getting steeper or less steep. So that's my issue in the fact that, you know, if I said, okay, find the gradient of y equals x squared, which obviously is my parabola, I can't just give myself an answer of m equals 2 or m equals 6 because it's not constant. It will depend on the point at which I'm looking at. For example, if I looked at the point where x equals, let's say here, which is what, about 3.1, then obviously that would be steeper than at the point of x equals 1. Likewise, if I looked on the other side, it's a bit hard to see because it gets cut off there, but the steepness of that line would be a negative value. Okay, so it all depends on the actual point that I'm looking at on my curved line. So there can be lots and lots of different answers. We can give a general gradient, formula for the gradient, and then we can substitute the x values into that formula to find out what the gradient is at that particular point. Okay, so this is why it gets a little bit tricky. Now, what we have an issue of is the fact that we've said before, finding our rise over run, and that's our gradient. Okay, we know that gradient is found by doing our rise over run, or changing y values or changing x values. We're always dealing with two coordinates. But if you look at the method we're looking at with a tangent, because that's how we're able to tell how steep the line is at that point, there's only one coordinate. That gives me an issue. Where's my second coordinate come from? How can I find my triangle and rise over run, or my changing y's over changing x's? It's very difficult. So what you've seen here, I've actually constructed a line, okay, on the parabola. So now I've got 2 points. Now, although that straight line is not the same value as my tangent, okay, what we'll be able to do is estimate what my steepness at that point is going to be. Okay, obviously if I take points closer and closer and closer, I'm going to be becoming more accurate. We'll talk about that in a little while. So we want to call this point xy, but remember I don't like to use the y value, so I'm going to call it the value of x and f of x. That's my coordinate there. Now this is the graph, f of x is equal to x squared. Okay, so what would this point be called? Well, we don't really know what this value is here, so let's make up a value of h. Okay, a height or a length or whatever you want, whatever you want to have. I'm going to use h. So this value, this coordinate here, or if that's x, then this must be x plus h because this is x and I've added h to it. And remember, we spoke about the y value. Instead of writing it as y plus h, okay, we know we just substitute in that x value there. Okay, the x value is x plus h, so it's f of x plus h. Okay. Something that you'll see, if I look at my rise over run here, as I said before, that line there, it isn't exactly the same as the green line. It's not the same as my tangent. What I'm actually going to look at, I'm going to look at a model here, if you can see this. That's my line that I'm making a point there. So, for example, I could have my point there. You can see that those two lines are not very close together. Now remember that the length between these 2 points is h. What you notice, as I go closer and closer to the actual gradient of my tangent, what do you notice about the h value? Hopefully you'll notice that the h value is getting closer and closer to nothing at all. So realistically, when it gets to the point, let's say, well, where h is 0, theoretically, that line's going to be like that. Okay? So, how does that help us? Well, let's go back to the rise over run model to start off with. Okay, rise over run. Just going to use it a little bit closer format here. So again, we said this is the point x So this is the point x comma f of x. Sorry about that. And we said this is the point x plus h f of x plus h. So we said here that obviously my rise over run, my gradient is my rise over my run, or my y2 minus y1 over x2 minus x1. So if we use that second model, my y2 minus y1, well, we've got f of x plus h minus f of x, so y2 minus y1, over my run, which is my x plus h minus my x. Now I can simplify this slightly because x minus x disappears. So I'm left with f of x plus h minus f of x all over h. And that is actually what we call our gradient function of a curve. Nearly. There's a little bit more to it. From that last model, as we said here, that the closer that h gets to, that height, we know that's our height, the closer that gets to 0, the more accurate my answer is going to be. So what we actually say is that, to finish off my formula, the limit as h approaches 0, f of x plus h minus f of x all over h is equal to my gradient. Or we actually say f dash x, okay, which is called the derivative function of fx. Okay. So let's have a look at this again. The formula. Now, again, this is called differentiation from first principle. Because this is how we did it originally. Okay, there is a shorter way, which we'll look at in sort of future lessons. But we say that the differentiation, so f dash x, which means the derived function, is equal to, as the limit h approaches 0, because h gets smaller and smaller and smaller till it's pretty much absolutely 0, we say that f of x plus h minus f of x all over h. Okay, so that's what we have to remember. And again, that comes from our rise over our run, okay, because it's the gradient. That's the whole idea of this, is trying to find the gradient from first principle. So let's have a look at a bit of a question here. Let's say we want to find the gradient of f of x equals x squared plus 3. Now remember, we can't actually just come out with a single value unless, of course, we're asked to find the gradient at a particular point. But at the moment, we're just asked to find an equation for the gradient, or an expression for the gradient. So a general rule, I guess. So let's have a look at this. So f of x is equal to, as the limit h approaches 0, now we need to have f of x plus h minus f of x over h. Now we have f of x, we know that equals x squared plus 3. What we don't have is f of x plus h. So we need to find that very quickly. Now we can do that nice and easily, because all we're doing, instead of having the x in here, we're going to replace it with x plus h. So I've got x squared, so I'm going to put x plus h where the x was, plus 3. So again, I'm simply just putting x plus h where the x was. Now let's just simplify that. If I square this, okay, we get x squared plus 2xh plus h squared plus 3. So now I have everything that I need. So the function x, f dash x, or the derivative of x, as a limit h approaches 0, f of x plus h is this bit here, x squared plus 2xh plus h squared plus 3. Now it says minus f of x. So minus x squared minus 3. Because remember, that's the same as doing minus x squared plus 3. Okay, I'll just expand that in one hit. All over h. Now we can simplify that again. Now x squared minus x squared disappears. Plus 3 minus 3 disappears. So I'm left with 2xh plus h squared all over h. Now that again can simplify further, because h goes into h once and it goes into there once. So we're left with 2x plus h. Now finally, we've said the limit as h approaches 0. So what we're going to do, instead of having the h here, we're going to replace that with 0. So 2x plus 0 is simply equaling to 2x. And I've found the value of my gradient for the graph f of x equals x squared plus 3. Now it isn't a single value, because remember we've said that looking at my particular parabola, which would be something that looks like this, okay, the slope or the gradient of my line is going to be different at any given point. For example, at that point there where x equals 0. Well, let's have a look. If at the point x equals 0, 2 times 0 equals 0. And look, that's what the gradient would look like. If I took the point, let's say x equals 1. 2 times 1 equals 2. If I went a little bit higher and did the gradient at x equals 10, 2 times 10 equals 20. And that makes sense, because my gradient would be much steeper. What if I took a negative value? Let's say negative 2. So the gradient, when x equals negative 2, 2 times negative 2 equals negative 4. And again, that would make sense, because my gradient would be negative, it would be going downwards. So once I've been able to find the general rule or formula for my gradient of that particular curve, if we are then given an x or an x coordinate, we're then able to substitute that in order to find out what the value of the gradient is at that particular point. Now look, this is a very a difficult concept to grasp first of all, I suggest you have a look at all the different videos that are out there. Again, Sal Khan has some brilliant videos there. Look through your textbooks. I'm going to do a whole pile of questions in my next lesson on finding the derivative or the gradient of a curve at a particular point. Lots of different questions there. So go through the next couple of lessons. Let me know if this has helped you. Please let me know if it hasn't, if it's been a bit confusing, because I can definitely try to redo this again and try to make it a little bit clearer. Look, thanks for listening, guys. Hopefully this has made some sort of sense to you. As I said, feedback would be fantastic. Just let me know if things I can sort of work on in this video. Have a great day, guys. Thank you.